Hello everyone, my name is Shai. I am currently a postdoc from Professor Hongguo's group at McGill University. Today, I will talk about electron-phonon scattering in low-dimensional field effect transistors from first principles. From the 50 years of microprocessor trend dataset, we can clearly see the transistor counts continue to follow an exponential growth. For example, more than 5 billion transistors can be integrated into the current 5 nanometer processing technology. However, on the other hand, we observe the flattening of the energy efficiency curve. A more concrete example, if we maintain the improvement trend for the efficiency, when we achieve the zeta scale of the supercomputer, we require the power almost to the same scale of a nuclear power. So that is probably too much. Energy consumption has become the largest challenge that we have to overcome if we want to maintain the historical rate of performance improvements. There are lots of aspects one can work on to improve computing efficiency. One thing that we can contribute here is to design low-energy switches from the atomic scale. Let me quickly go over a schematic of a typical field effect transistor that consists of a gate, a source, and a drain. So how much of a gate voltage is required to turn on the drain current is critical to the performance and power consumption. It is formally defined as this formula. So we want this slope to be as steep as possible because the steeper this slope will be, the smaller voltage required to increase the current by tenfold. However, there's a limit for this slope in the conventional MOSFET at room temperature. This is due to the Fermi-Dirac distribution. The electron density from the source is the product of the denser states and the Fermi-Dirac distribution function. A small fraction of electrons have sufficient energy to surpass a barrier, the so-called Boltzmann tail. This Boltzmann tail causes substrate leakage and causing the substrate swing larger than 60 millivolts per dec at room temperature. To reduce this leakage, one strategy is to modify the density states of the source. As the density states in graphene decreases linearly near the Dirac cone, it results in a super exponential decay of the charge density above the potential barrier, effectively reducing the thermal tail. Consequently, the Dirac source FETs allow for a steeper SS in comparison to conventional FETs. In experiments, the steep-slope Dirac source FETs have been successfully demonstrated at room temperature within graphene carbon nanotube and graphene MOS2 heterostructures. However, the origin of the steep-slope switching remains controversial. Theoretically, the steep-slope switching is due to this p-type graphene Dirac source, because the density of states is linearly decreased when approaching to the Dirac cone. Ideally, electrons preserve their coldness before reaching to the top of the barrier. An N-type graphene is usually applied to lower the Schottky barrier height. Researchers question that inelastic scattering in this N-type graphene semiconductor heterostructure will destroy the cold Dirac source and rethermalize the electrons. It is not a trivial task to consider the electron-phonon scattering effect. One conventional method is to introduce a fictitious contact which gives an additional self-energy of electron-phonon scattering. Within the Born-Oppenheimer approximation, the self-energy due to electron-phonon coupling and the full electron screen function is calculated self-consistently. However, it is very hard for this method to include electron-phonon coupling beyond the molecular scale. As you can see that we have electron-phonon coupling matrix here, and we also need to solve the full green function self-consistently. And they are very computational depending. Here we seek another method. This method is even more intuitional. We don't use the self-energy of the electron-phonon scattering to create this random potential. Instead, we use the configurations with certain displacement to produce this random potential for electrons to include this electron-phonon scattering effect. We use ZG method to generate these configurations. Next, I will show result based on these different configurations. Using the ZG method, we can generate configurations at various temperatures. We can first take a look of the pedals of the heterostructures at equilibrium at different temperatures. With the increase of temperature, we observe peak broadening. Generally, in the peak point, the dose decreases, and at the valley, tensile states increases. The gap contributed by tungsten diselenide decreases, while the pedals contributed by the graphene didn't change too much. Now back to the device. Our device can actually be separated into two regions. In one region, we have a tunnel barrier. In another region, we have a thermionic barrier. Notice that the tunnel barrier intrinsically included in the device structure is not demanded to play any role in the switching process. It is this thermionic barrier region that is responsible for switching, as in MOSFET. But the steep slope switching properties of the device are still driven by the tunneling barrier region. It provides an energy filtering effect as in tunnel FETs. These are the electronic structures of these two regions. We first look at the calculated IV curve of the thermionic part of the device. You can see that with scattering, in off-state, electron-phonon increases current, while in on-state, the phonon reduces current. This trend roughly matches with some experimental results of similar kinds. Let's first analyze the off and on state of the thermionic region in detail. The dotted lines are those with scattering. You can see the shift bend edge possibly leading to an increase of the transmission in the bias window in the off state. When we continue lowering the barrier in the channel, we are in the region where the transmission undergoes more pronounced changes than those, which lowers the on-state current. Let me use a simple cartoon to illustrate this. In off-state, the little tail here helps increase the off-state current. In on-state, since the dose smearing out, the peak dose reduces when the T increases. Thus, the on-state current reduces. It is not only the tensile states play a role here. We could analyze the scattering matrix to see temperature-dependent transmission on each channel. You can see when temperature increases, there are more channels responsible for transmission in on-state. Another thing we can observe is that in on-state, the transmission in each channel reduces when including the scattering, and it is the opposite of the off-state. This result at least shows that our method is an effective way to modifying the barrier between inelastic tunneling events, and in this way, we also include some inelastic scattering effect. Comparing with the thermionic part of the tungsten diselenide only device, the IV curve of the whole direct source device when considering scattering shows an increase both on and off state of the current. This can also be clearly seen in the transmission trend of the two regions. For the tungsten diselenide only thermionic part, transmission decreases with considering scattering, while for the tunnel region, generally the transmission increases. So why is the transmission enhanced by phonon scattering in the tunneling region? A potential explanation is that the distortions introduce extra channels between the heterostructures. We could also look from the K-space. We can see phonon scattering enhances transmission at the Fermi level as temperature increases. This result might be related to other views that a scattering effect could change a mismatched transverse momentum, leading to a relaxation in the transverse momentum selection. Here is a quick summary of today's presentation. We utilize tungsten diselenide and graphene heterostructures as direct source for decreased substrate swing and increased power efficiency. We integrate the electron-phonon scattering effect into the NEG-FDFT method using the ZG approach to assess the effect of the phonon scattering on the direct source. Our study examines the impact of phonon scattering on the direct source FET device across real space, K-space, and energy space in both tunneling region and thermionic region. The results indicate that electron-phonon scattering does not significantly compromise the overall performance of the direct source FET we study here. Last but not least, I would like to sincerely thank my supervisor, Professor Guo, and all the group members, and I would like to acknowledge all the funding agencies. Thank you very much for your attention. Thank you all.